Hello, everyone. Thanks for joining us today. Welcome to the Quality of Service Workshop Series sponsored by Action Pack Networks. My name is Steve Adams. I'll be your moderator today. Today's session topic is Quality of Service for Medianet Simplified. We're very pleased to have Mr. Tim Szigeti from Cisco Systems as our featured speaker today. Tim is a Cisco Certified Internetwork Engineer and is a Senior Technical Leader in the Strategic Architecture and Strategy Unit at Cisco Systems. His role is to design network architectures for the next wave of Medianet applications, including telepresence, IP video surveillance, digital media systems, and desktop video. He has also specialized in quality of service technologies for over a decade, during which he has authored many technical papers, as well as the Cisco Press books, End-to-End Quality of Service Network Design and Cisco Telepresence Fundamentals. The session today will run about 2 hours. Tim will discuss the driving factors necessitating quality of service network design updates. This includes new applications and business requirements, new industry guidance and best practices, and new platforms and technologies. He will present Cisco's quality of service strategy for Medianet and will also cover campus and WAN-specific design considerations. We'll then wrap up with a Q&A session. And now I'd like to turn it over to Tim Szigeti.
Thanks so much, Steve. So I really appreciate this opportunity to share some of the latest work that we've done, and we've actually worked in conjunction with Action Pack on the QoS design and management products on both levels. This presentation is around the work we've been doing in simplifying Medianet QoS. For now 4 generations, we've produced in-depth quality of service solution reference network design guides, or SR&Ds. More lately, we've called them CVDs, Cisco Validated Designs. And these documents are several hundred pages in length, and they cover all the platforms and all the main design options and all the configuration level detail and all the troubleshooting and verification detail, et cetera, et cetera. They get quite unwieldy, and so sometimes when we share them with network administrators, it's not uncommon. We get feedback saying, okay, it's good information, but it's a bit overwhelming. So this specific prezo that we're going to be going through today is sharing a new type of collateral aimed at simplifying the designs and the recommendations for QoS specific to the needs for rich media networks. Our agenda specifically, we're going to look at the QoS design strategy and the basis for our recommendations, and looking at various relevant RFCs, also in the direction in which these RFCs are headed. Then we'll look at campus-specific tactical designs. What do you need to know that's unique to the campus environment when it comes to quality of service? And then we'll go through a series of platform-specific designs. We're not going to go we'll share all the config level detail, but we're not going to be drilling down into it simply because of time constraints, but the configurations, even in that level of detail, are included in this prezo. But as Steve already mentioned, there are compatible templates in the Action Pack software, so while the configs will be presented, there's really no need to drill down into line-by-line level detail. Then we'll turn our attention to the branch, WAN and branch, and look at those unique considerations to that place in the network. What's different? Things such as we're using different types of QoS now. It's iOS-based QoS as opposed to hardware-based QoS in the campus. What are some of the unique tools there, and how do they interrelate, and how does that all come together to make the overall best optimal policies for this area in the network? And then we'll look at applying those recommendations on the 2 main platforms, ASR for WAN aggregation, and then ISR G2s for branch routers. And then as time permits, we may even go through the Auto-QoS for Medianet feature. This is a feature that is to update QoS, the Auto-QoS feature, which has been around for about a decade now, but has been on the Catalyst platforms limited in context to deploying voice over IP telephony only. So some advancements there to expand the scope of that feature and its permutations, and we can share that as well as time permits, like I say. So before we get into the details of our various design recommendations, it's important to step back and to understand why. Like, why do network administrators need to take a closer look at their current QoS deployments, and why may they need to make changes either today or shortly down the road. To this end, we've kept very much lock in step with the research that's been done with the Cisco Visual Networking Index group of studies. If you guys are maybe not familiar with these studies, they're fantastic. If you go to cisco.com/go/VNI, Visual Networking Index, that's a short jump link to where these studies are hosted. And some of the highlights from these studies, basically, from the largest enterprise customers globally, as well as, Tier 1, Tier 2 service providers collecting all these stats and doing the trending and analysis, we come up with some really interesting patterns and projections. For example, global IP traffic continuing to exponentially increase by the end of 2015. The number of IP devices being more than twice the global population by the end of 2015. Wireless traffic will actually be more prevalent and will finally exceed wired traffic by that time as well. As well as there's a series of non-PC traffic that's really making inroads into the workplace and the consumer place, like tablets, smartphones. So all this non-PC traffic is accounting for 15% of the global IP traffic by the end of 2015. And to achieve this, it's basically increasing by an average of 150% per year to reach that number. So even though 15% of the global pile may seem like a small slice, the rates that they're accelerating yearly to gain that share is, like I say, about in the order of 150+% per year. There's not only a major increase continuing in the volume of traffic, but also a dominant shift. For instance, for the last 10 to 12 years, well, actually, sorry, the last 10 years, let me be correct, the dominant types of traffic on the Internet backbone as a whole was peer-to-peer applications. So starting from the days of Napster, all these types of file-sharing applications, Napster, Grokster, Kazaa, BitTorrent, Morpheus, all of these have continued to dominate as the largest application by volume over the Internet. However, that's been displaced by video-based traffic by the end of 2010. So video-based traffic for the first time ever, and it took 10 years to dethrone peer-to-peer flows as the dominant types of traffic, and it's continuing to increase. It's projected that by the end of 2015, 90% of all consumer traffic will be video. And as far as enterprise traffic, we see very similar patterns. For example, in Cisco IT, across our own backbones, we've done some samples, and we've seen that video traffic now accounts for 66 to 70% of our current flows across our enterprise network. So this trend is definitely affecting the workplace as it is consumer networks. And so network administrators have to be aware of how to provision for these rich media applications. Another level of complexity then that administrators face is that as these applications continue to evolve, they're no longer fitting into neat little buckets of voice, video, and data. Rather, what we see is that there's a plethora of applications on our networks that combine these various media types, voice, video, and data, and many of them might be rolled out and sanctioned by the IT department, but there may be quite a number which are appearing on our networks that are completely unmanaged, just users demanding support for these various types of applications with or without the official IT department providing that. For instance, in-house in Cisco, we had basically a YouTube type of initiative launched where engineers would share information, and they called it C-Vision, Cisco Vision originally, and just where engineers would post various videos, and it made a lot of sense. It took a lot of storage space, networking space, etc., and then eventually our IT department had to take it over. So these type of unmanaged applications are increasingly common, even on enterprise networks, And that has to be accounted for, as well as the fact that most of today's applications, rich media applications, have a variety of these components. So the network administrator then has a very difficult choice in how to provision and accommodate these applications. Does he, for instance, he or she say, well, if it has a voice component, well, in order to protect that voice component, I have to put all this application into voice. For instance, we're using WebEx. We have, audio component. We have data sharing. Optionally, we could even have a video subcomponent. So how should a network administrator provision WebEx? This is a challenge. So if he puts it all into, say, data, because data is the dominant flow, well, then the voice quality may suffer, or the video, vice versa. Whereas if he puts it all into the video or voice queues, well, then because of the amount of data that's being transferred as well, that might overwhelm, and it might be difficult to accurately provision the amount of traffic required, as well as to provision call admission control, because several of these applications don't have these capabilities. So these are the problems, the relevant problems based on the internet trends and the application trends that many of our network administrators and customers that we're dealing with have been facing. So how to go about addressing them? Well, Cisco's always been an advocate of following standards and RFCs because this generates greater consistency, it allows for greater interoperability, and it basically, when it comes to QoS specifically, it will improve the overall quality of service end-to-end, even beyond the administrator's area of domain and their boundaries. Because as they hand it off, as their traffic off, well, they can be relatively confident that if other providers or partners are also following the same standards or RFCs, then the traffic will be continued to be treated in a uniform and consistent manner, and therefore improving the overall end-to-end QoS beyond their administrative domain borders. To that end, there's a very relevant RFC. It's RFC 4594, which for the first time has associated various standard per-hop behaviors with specific applications or application classes. So for instance, in the past, we would have various RFCs, standards that would say, okay, let's take an example, RFC 3246, that says this is an expedite forwarding per-hop behavior. In general terms, it just means it's a strict priority queuing service. Whether it's implemented in hardware, whether it's implemented in software, it doesn't matter. That's up to each vendor. But the service is, if there's a bottleneck, packets marked to EF, which is expressed as DSCP46, will come to the front of the line. That's the behavior. But in the RFC, again, I'm referring to RFC 3246, there's no mention of what application should receive that service. So even though this behavior was defined, so many people, have differing views. By and large, the norm has been to put voice into this class of service. That's been the norm for about a dozen or more years. However, like I say, there's no standard or no RFC that actually made that connection. And there's some customers that say, you know what, that's not our dominant critical application. We worked, for instance, with a hospital group in New York City, and they were basically provisioning their network, and their most critical service was robotic surgery, where a surgeon in one hospital would be performing an operation on a patient in a completely different hospital via the network and using robotic arms. So they're like, this is more important to us than voice over IP. So that's what's going to get the EF service. And we had to agree with them, especially if we're ever going to be a patient or something like that. You'd want that kind of provisioning in place. So returning to RFC 4594, this is the first time, again, that there's been an RFC that's linked the per-hop behaviors to various application classes. 12 classes are called out and expressed in this RFC. The first point I want to make, and I'm going to come back to it on the next slide, is that in no way does this mean that anyone has to deploy a 12-class model today. That's typically the first feedback we get, is people saying, oh, it's just way too complicated, too complex for me today. No, this is an informational RFC. It's not a standard. It can be implemented in whole or in part or not at all. It's up to any given administrator to do that. Therefore, just because there's 12 classes of service, you can use any number of subsets of this and still be in conforming with it. The classes that are outlined here: broadcast video, we use that for IP video surveillance. It's unidirectional, real-time video, especially for high-def video streams when there has to be response to an event in progress, something like that. We find that there are a lot of customers are very much requiring this service if they've deployed IP video surveillance. Real-time interactive is now a bidirectional flow of multimedia traffic that obviously, as the name implies, requires a real-time service. This class of traffic we've used extensively for our Cisco telepresence systems, and it's proved to be a very effective fit. Then we have two compatible classes for multimedia conferencing, bidirectional flows that don't necessarily require real-time service, but at least a bandwidth guarantee. So for any other type of bidirectional flow that's not real-time, we use this, for instance, for WebEx, Cisco Unified Personal Communicator. We also use these for some of our timbre products, like EX90s or similar, where there's not quite the user level of expectation and quality needed as, say, a room-based, several $100,000 teleconferencing system like telepresence. The next class of service is multimedia streaming, and again, this is a unidirectional flow similar to the broadcast video class, but not requiring a strict priority real-time service. We have a few control classes that are outlined in green. Network control, which includes routing protocols or other types of HSRP packets or anything that helps keep the network control plane up, is typically marked by default on our routers as class selector 6. Signaling traffic is then the same type of traffic but for the IP telephony or IP video telephony infrastructure. And then we have an OAM class, operations, administration, and management, for basically products like ActionPact or any other types of traffic that's going to be polling, updating, configuring, collecting MIBs data, any operation like that. There's two data classes that are called out. Transactional data, this is types of data that users are dependent for a response via the network in order to continue working. We call these in general foreground applications, as opposed to the next data class, which is bulk data. Anything that's a background application is suitable for this class. So this is machine-to-machine traffic, whether it's anything from email to content distribution to database backups or PC backups, anything that a user is not directly impacted from their work but can operate in the background. And typically these are long TCP-based sessions and flows, and they can really dominate a disproportionate amount of bandwidth due to the nature of these protocols, and therefore you'd want to constrain them in the event of bandwidth being scarce, and you want to make sure that your foreground applications would receive a superior level of service. Our best effort class, and then also what's gained a lot of popularity in the last, I'd say, 8 to 10 years, is the idea of a scavenger class, a less than best effort service. So this is for everything else that's on the network that really doesn't contribute to the bottom line objectives of a given enterprise or organization. And it's just a matter of, people, bringing their machines in and saying, well, I can access, much faster bandwidth at work, so why don't I do my BitTorrent downloads, my YouTube or, gaming stuff, whatever it is, entertainment-oriented applications typically, but on the production network. Administrator has a choice here. He can either shut them down entirely, and that's typically a very unpopular choice with the user base. Politically, can have a lot of ramifications. Or what seems to be a better compromise is provisioning these in a less than best effort service, saying that, okay, if there's bandwidth existing, we'll allow it, but in the case of congestion, that class is dropped the most aggressively, and there's no implied good faith guarantee of service with that class of traffic. And that seems to be a pretty acceptable compromise with most user bases. That being the case, there's only one deviation that Cisco has made with RFC 4594. In this RFC, it recommends marking call signaling traffic to CS5. We've been marking call signaling to CS3 for about 10 years now. We already had to make one call signaling marking migration. We originally, for those of you that have been doing IP telephony for a long time, you may remember that we originally marked call signaling traffic to AF31. AF31 was a poor per hop behavior for signaling traffic because anything marked to an assured forwarding class, by definition of the standard, is subject to policing, remarking, and then aggressive dropping via DSCP weighted read. Well, we don't want to be policing, remarking, and aggressively dropping call signaling traffic. This is control plane traffic. It will result to delay to dial tone and calls not completing or not connecting or not hanging up, things of that nature. It's control plane traffic, and therefore we made that marking migration to class selector 3. To do that, it was a very expensive, lengthy, and painful process, and lacking a compelling business case, we're not going to put everybody through that again just for the sake of 100% compatibility. Like I say, this is an informational RFC. It can be adopted in full or in part. That's the only deviation we as a company have been making in adopting this strategic direction. Coming back to the point I made is that in no way does any given company need to deploy a 12-class model at this time. However, it's very advisable to be looking ahead. For instance, when we wrote our last QoS SR&D back in 2004, 2005, there was only 2 classes of video. There was interactive video and streaming video. Things like telepresence didn't exist, IP video surveillance didn't exist, digital signage didn't exist. None of these applications, were even thought of at the time. But as more and more applications, become available, these have unique service level requirements, and then if they're viewed as mission critical, business critical applications, the only way to guarantee unique service level requirements is to give a dedicated class of service for various application class. And so this is an evolution that we're going to see continuing. For example, there's even people in the IETF right now that are making proposals to update RFC 4594 for expanding the number of classes. We've already hit limits with that. And so I think the next set of drafts have a proposed 26 class model. And so we can see that this evolution will likely continue just simply given the nature of technology and for increasing business needs. That's not to be overwhelming, that's just to advise to be forward-looking so that you can think about, okay, if I'm going to be deploying these additional classes of applications, what code points am I going to use for their marking? How will I continue to subdivide the bandwidth so that I'll be able to accommodate them in the future, and so on and so forth. Provided a lot of guidance in this in our SR&Ds and in the papers we're going to be discussing. But for the key takeaway here is that most customers we work with are between a 4-class and an 8-class model. Even ourselves, Cisco IT, is at a 7-class model. So don't feel that when you see these full 12-class models being presented that means that's the way to do it. It's not. It's just that's showing how even taking a complex, forward-looking model, here's a solution, and then that can be pared down and simplified to a given organization or business need. The number of classes of service you deploy are a pure function of your business need, not your platform's technical constraints, not the number of classes of service your provider offers, none of those things. It's just a matter of what does your business require from QoS. Does it require rolling out voice? Okay. If so, IP telephony, that's a minimum 3-class model, real-time, signaling, and everything else. Maybe you have a need for a less than best effort service. Maybe you also have a critical data class, etc. And these types of decisions, business level decisions, will ultimately dictate the number of classes of service you're going to be deploying end-to-end, your QoS strategy. So the discussion we've had so far can be summarized in this this single at-a-glance document. So at the link given below, there's a 2-page document that's intended to be printed on the forward and reverse side on a single piece of paper. And this is what we're expressing as QoS simplified. So rather than reading necessarily I think it's a 40-page introductory chapter that goes into depth on this subject, we have the link to those chapters at the end of the presentation. But if an administrator just wants, the 5-level key takeaways and summary of that, they can just click on this link here for this at-a-glance document, and then it's all presented there. This will be a running theme in this presentation. Each section will just have the associated at-a-glance document. So we're basically paring down, I think, about 500-odd pages of technical documentation to less than a dozen at-a-glance documents. So that's where we get the QoS simplified in the title. I'm going to move on to the next section, which is now looking at Medianet campus QoS design. So how do we now implement the strategy that we've come up with, the number of classes, how everything's going to be marked, so on and so forth, and apply that in our campus? Well, the first question that really has to be addressed, and some administrators still struggle with it, is saying, do I really need QoS in my campus? I'm so over-provisioned, so underutilized. If I look at my statistics, on multi-second basis, I see that I'm using a fraction of my capacity for the most part. It's important to realize, though, what is the role of QoS in a campus network? And it's not to control latency. Nowhere is QoS ever used actually to control latency. Latency is the delay it takes from the time a packet is put onto the network and it's received. That's purely a function of geography. How far is that packet traveling? And it may be a function of the clocking speed. Sometimes QoS is used to control jitter. That is the variation in delay that it takes from packet A to get from sender to receiver versus packet B to get to sender or receiver. That variation may be caused by network congestion or multipass or things like that. Sometimes QoS, especially in the WAN and branch networks, is used to address that. In a campus, jitter is in the microseconds. It's negligible. It's completely irrelevant, a concern. The real concern, especially when it comes to rich media applications, is controlling packet loss. For example, our switches, our Catalyst switches, we have very rich buffer sets on them, but because of the speeds of gigabit Ethernet and 10 gigabit Ethernet speeds, these buffers fill up very, very quickly. For example, if we look at, say, a 6148A line card, it has, I believe, 9 meg of buffers, and then if it's divided into the 4 queues that it supports evenly, any given queue could be oversubscribed within 10 milliseconds of sustained line rate burst. Now, video applications are very bursty by nature, and it doesn't take a lot to oversubscribe them. Similarly, some 10 gig line cards are 6716, even though it's got 90 meg of per port buffers, same situation. 90 meg of per port buffers, but now at 10 gig speeds, now at 8 queues per port, while it's still within 10 milliseconds, we could overwhelm any given queue, and you cause drops. Now, rich media applications, particularly high-definition rich media applications, say like telepresence, they're extremely sensitive to packet loss. They're 100 times more sensitive to packet loss than, say, voice over IP. We can say this because voice over IP, we've set a packet loss target of 1%. If you lose just one packet when it comes to voice over IP, you could conceal that. You'd basically just play out the last sample. However, with an application like telepresence, if you lose one packet in 10,000, it's visually apparent and discernible by the end user. So packet loss is exceedingly stringent when it comes to provisioning for rich media, particularly high-definition rich media applications. And incidentally, HD video has surpassed standard def video on the Internet as a whole, and that's also noted in one of the Visual Networking Index studies. So the key takeaway here is you absolutely need QoS in the campus to prevent instantaneous buffer overruns because of the speeds and the limitations of the buffers in the campus networks. That's a key takeaway, to prevent drops. Now, how do you go about turning on QoS in the campus? Well, in our Catalyst switch family, all QoS is performed in hardware. Now, there's some advantages and disadvantages of this. If it's performed in hardware, first of all, it's done at line rate without any CPU impact, so it's very efficient. The downside is, as the hardware varies, so does the policies, and often the syntax and the constructs. So that's why we have still a fair degree of platform-specific variation across our Catalyst switches. There are some initiatives to improve that consistency. We're very well aware of this customer feedback and challenge. The first initiative is to have full modular QoS, iOS across all our platforms. The first platform in our Catalyst series of switches to implement this is our 4500, SOUP 6E, SOUP 7, etc. However, that's also going to come on the other platforms. And then farther down the line, we're also looking at doing consistent silicon, so using the same chips across platforms with the same queuing, etc., and QoS capabilities. However, when it comes to strategically rolling out QoS today, these are the key takeaways. Always do it in hardware whenever you have a choice. So if you can perform classification, marking, policing, do it in the Catalyst hardware as close to the source as possible. There's no point letting traffic onto your network, only if you're going to drop it midstream. Get rid of that right at the edge. Mark it right at the edge, and then you can trust the DSCPs of those markings throughout your network. That's truly the principle of the DiffServ standards. That's RFC 2474, incidentally. When it comes to practical implementation, a few key things to keep in mind is that on most of our Catalyst switches, QoS is disabled by default. You can configure the policies, they'll show up in your config, you'll see them there, etc., but unless you globally enable MLS QoS, for instance, none of these policies will be active. So that's a key place to start. I've been bitten by that myself. Sometimes in the lab you get tired and you turn on all this stuff and you're wondering why nothing's happening and working properly. It's that global command that may not be active. We'll look at trust states. We'll look at the various ways QoS can be implemented, ingress and egress QoS models, all of these points on the subsequent slides. Let's start with the trust states. What does this all mean? Well, by default, once QoS is enabled, all switch ports that use MLS QoS, this is the 2K, 3K, the classic supervisor 4K, and the 6Ks, they'll be in an untrusted state. What that means is that regardless of whether there's markings at layer 2, 802.1p, or markings at layer 3, DiffServ code points, all those markings are going to be set to 0 as packet is processed internally, and then as the packet exits the switch, those markings will correspondingly be marked down to 0. If we elect to trust cost, then we accept the 802.1p marking. And not only that, but there's a mapping table that's applied that maps cost values to DSCP. It basically takes the cost value, and by default will just multiply by 8, unless that mapping table has been modified. So to convert from 3 bits of binary to 6 bits, you just multiply by 8, and that's exactly what the default behavior is. So if we have cost 5 and DSCP 46 coming in, and we elect to trust cost, well, that internal DSCP will be derived from the mapping table. 5 times 8 is 40, and therefore the packet will exit with its DSCP being overridden, but the cost value being accepted. Conversely, the third option we have here, really, I'm going to ignore trusting IP precedence because that's a legacy option, and we really don't recommend using IP precedence anymore. There's no reason to whatsoever. That's a legacy and obsolete technology. DiffServ code point is obviously the way to go. With 6 bits of granularity versus 3, you have much more design options, and you're not being constrained by an 8-bit model. I mean, a 8-class model. So we trust DSCP. Well, then we accept the code point, and if need be, the cost may be overridden to match the first 3 bits of the DiffServ code point. Another option at an administrator's disposal is conditional trust. And this is a dynamic operation that can be configured to occur pending a successful Cisco Discovery Protocol negotiation, a CDP negotiation. How this works is an endpoint, as it attaches or comes online, announces itself via CDP to the network switch. If the switch has appropriate policies for conditional trust configured on it, it'll say, okay, I will trust you either at layer 2 or at layer 3, however it's administratively specified. And while you are connected to me, I will accept your layer 2 or layer 3 markings and pass them on to the network. We can trust Cisco IP phones. We can trust devices like Cisco telepresence systems, Cisco IP video surveillance cameras, Cisco digital media players, etc., etc. You may be picking up on that this is a Cisco-specific feature, so it's dependent on the proprietary Cisco Discovery Protocol, and therefore, at this point in time, it's a Cisco-specific feature. So how should we implement our trust boundaries? Typically, network administrators have chosen not to trust PC endpoints, regardless of whether they're able to mark their own code points. These may be centrally administered, and there's some models that allow for that to be secured, and so the user can't tinker with it. But the general feeling, even though that kind of technology and solutions have been around for, I'd say, about 6 or 7 or more years, really we haven't seen hardly any administrators just accepting trust from endpoint devices. It's just too much of a potential vulnerability, because then if the users realize that somehow they're able to mark their flows or get around any administrative lockout in marking flows, then they can just mark any flows they want and hijack their way into queues intended for priority servicing of voice or video. For any type of conditional trust endpoint, we use the MLS-QoS trust device. That's a conditional trust keyword, and then whatever the device happens to be. When it comes to implementing our policies, we have a couple of options available to us. We can apply QoS policies on switch ports themselves. A physical switch port may be applied with a specific service policy. Regardless of what VLAN that switch port is operating in, it's bound to that port. Some policies might scale better, such as marking policies may scale better if they're applied to a logical interface, such as a VLAN interface. So for instance, traffic arriving on a voice VLAN might be given a certain policy versus traffic arriving on a data VLAN or a guest VLAN. In such cases, the policy could be applied on the logical VLAN interface and not the physical port. Like I say, this may make scaling a little more efficient. Policing policies we do not recommend to be applied on a per VLAN basis, especially if they're policing on an aggregate, on an aggregate basis. For instance, if you say, okay, I'm going to police endpoints on the voice VLAN to 128K. Well, if that policy is applied to the VLAN as opposed to a physical port, then all traffic received from any number of physical switch ports that are belonging to that logical voice VLAN, the aggregate number of traffic will be policed to 128K. and that's not the behavior of a policer or the intended behavior of such a policer. It's typically more in line with wanting to police on a per endpoint basis. So to achieve that functionality, there is a hybrid option, and the best implementation of this is on the 4500 series, and that's per port, per VLAN QoS, where basically you can set a service policy on a trunk switch port that is carrying, say, traffic from a voice VLAN, a data VLAN, possibly even a guest VLAN, and unique policies can be applied to each VLAN on a specific switch port. This makes for very granular use of, say, per port, per VLAN policing. You can make sure that on a given switch port, if traffic is from this VLAN, it will not exceed this amount of traffic. So very, very granular option available, and like I say, really on the 4500. It is possible to do on the 2K, 3K, but it's wildly complex. It requires hierarchical QoS policies, nested policies to achieve this. So technically it's feasible, but practically I wouldn't recommend it. It's just too complicated. We document the solution in the SR&D, but really this is an option that I think is best suited for the 4500s. Okay, so putting it all together, what do our ingress QoS models look like in the campus? Well, it can be anything from the simple, just a basic trust policy, to something a little more complicated, saying I might have some policies that will explicitly match and classify traffic based on layer 2, layer 3, or layer 4 criteria, and then I will explicitly mark them at the edge. I may then overlay even a set of policers. This is showing how the policies can continue to increase in complexity. And finally, I might apply policers on a VLAN basis. I might have a set of policers on a voice VLAN, completely different set on a data VLAN. In our design guides, we show all of these policy options, from the simple to the complex. Somewhere in there is going to be a policy that will be suitable for, I'd say, 80 to 85% of administrators requiring QoS. And finally, on some platforms, there's a need for ingress queuing. When the sum of all traffic that could potentially enter the switch on all the switch ports exceeds the amount of bandwidth that the backplane offers, then we have to implement some sort of ingress queuing policy to arbiter how traffic is going to get on and contend for that backplane resource. For instance, if we started using 3750 switches and we started stacking them, well, the backplane is basically two dual counter-rotating 32 gig rings, so effective backplane is 64 gig, but as we start stacking switches, we could easily exceed the potential traffic entering the switch versus the backplane capacity, and in such scenarios would highly recommend enabling ingress queuing policies. Egress queuing policies are also critical at every single switch port that has a potential for oversubscription. We recommend some basic guidelines here, and that is to provision no more than 1/3 of a given link's capacity for real-time traffic, no less than 1/4 of a link for best effort. You have to realize that even though best effort might seem pretty low on the overall hierarchy of application classes, it does represent the bulk, the majority of your traffic by number and likely by volume. For example, most enterprises we work with have well over 1,000 applications on their network. Of those thousands of applications, is going to be a very small minority that might be given preferential service or possibly a deferential or less than best effort service, but the majority are probably going to continue to remain at that default best effort class. So it has to be adequately provisioned. In our Catalyst QoS feature set, we express our queuing structures by this nomenclature. We call it 1P, XQ, YT, where 1P represents a single strict priority queue. For instance, 1P 3Q 8T. Let's use that example. 3Q means in addition to the strict priority queue, I have 3 non-priority queues. Each of those non-priority queues has a certain number of drop thresholds. In this case, 8 drop thresholds per queue. So I can really implement a lot of differentiation in service even though I have a limited number of queues at my disposal. We recommend no less than a 1P3Q queuing structure for provisioning for Medianet, and these recommendations that I've already addressed about real-time and best effort and so on and so forth. If a congestion avoidance mechanism like weighted red is supported on our platforms, then we also recommend enabling those features, especially on TCP traffic classes. Those are the classes of traffic that will best be suited for it. Now there's one final twist when it comes to deploying QoS policies, and again this is kind of one of those physical versus logical considerations that we've already talked about when applying policies on a per port basis or a per VLAN basis. What happens when ports are bundled into ether channels? How should we go about applying QoS policies? Do we apply it on the logical interface, the ether channel bundle, or do we apply the policies on the physical port members? Well, unfortunately, the answer is it depends. It depends on the platform. Queuing policies, egress queuing policies are always applied on the physical port members, but ingress policies might vary. On the 2K, 3K, these are applied to the physical port members. On the 4K, 6K, ingress QoS policies are applied on the ether channel interface. So as we go through platform by platform recommendations, you'll see this final consideration, pop up as a reminder to show, okay, administrators, if you are going to be doing some QoS, how should you be doing it if you're running it over ether channel? Let's put it all together. How do our policies look like once we put everything together in our campus? Well, the policies that vary the most are the access edge policies, and those will vary according to the endpoint that we're connecting to. Either they're untrusted, statically trusted, or conditionally trusted. Those are the main design options. We could have some optional marking or policing policies, but once we've defined our trust boundary at the edge, then we can trust DSCP throughout the rest of the network, and all we have to do is implement queuing policies, typically egress queuing policies. So now all these considerations unique to the campus are summarized on this at-a-glance document. So this goes a long way then in paving the way for the platform-specific implementations of the overall QoS strategy, complete with campus-specific considerations. The next couple sections will then be platform-specific. So if in the campus we're deploying QoS on a 3K, what do we need to do? I'll be going a little bit faster, I think, in this section, in these platform-specific sections, simply just to highlight the key features. On a 3K, the typical role for a 3K in a Medianet campus is at the access edge. It can be connected to conditionally trusted endpoints, untrusted endpoints, or even trusted endpoints. All three options exist. For uplinks, these would be statically trusted for DSCP and queuing policies on all of these switch ports. 3 main steps to enabling to configuring QoS on the 2K, 3K. First of all, explicitly enable QoS. Choose your ingress QoS model. And there's 3 main models to choose from. And then configure ingress queuing. And there's a 4th step, egress queuing. So ingress queuing is unique, especially to the 3750. That was the one that this is going to be the most relevant on. Ingress queuing is not supported on the 2960, just as a heads up. And the 3560, well, typically the oversubscription ratio is so nominal that may not be required in most cases. The configuration syntaxes for enabling QoS, for trusting DSCP or doing conditional trust, these are all highlighted. The presentation that I've used throughout this deck is basically having shaded commands global and then yellow highlighted commands as interface specific. So that's by far the norm. I think there's one exception, and that's when we get to the 6K, but the legend is shown on each config example. If we want to define explicit policy maps, service policies, well, these are illustrated here, globally in gray, and then a single service policy input statement on the interface. Ingress queuing, we only have 2 queues that we can work with, but we can still efficiently map to these 2 queues. We want to put voice, broadcast video, and real-time interactive. These are the 3 applications that may be configured with a expedite forwarding a per hop behavior per RFC 4594. That means they may be given strict priority service. Okay, that being the case, we put that into the strict priority queue. The remainder of the applications we put into the non-priority queue, but we'll use the thresholds available to us to protect the control plane traffic for the network, followed by the control plane traffic for the IP telephony or video infrastructure, and then finally everything else. The configurations follow. And then the egress queuing model, similar logic, but the queue numbers have changed. Now Q1 is our strict priority queue, and so we apply the 3 applications, voice, broadcast video, real-time interactive, into it. We protect our control plane traffic and our guaranteed bandwidth queue. We can also have a dedicated default queue, a best effort queue, and then we have a bandwidth constrained queue for bulk and scavenger traffic. Remember, these queuing policies only engage when there's congestion. So if there's congestion, we have to start making drop-in decisions. What traffic should we be dropping the most efficiently or most aggressively? Well, scavenger traffic, followed by then bulk data traffic. Those, because they're TCP-based flows, they can adapt to drops and adjust their segment sizes accordingly. And since they're background applications to begin with, no users are directly impacted. The queuing policies follow, and so on and so forth. When it comes to Ether channel QoS, all the policies are configured on physical port interfaces for these platforms. That's the guiding rule. And then here's the 2-page at-a-glance summary. If you want to, get up and running to turn on QoS for Medianet on these switches, this would be a good place to start, just to review the key, the roles, the steps, the overall designs, and then either cut and pasting from the configurations on the back or making use of the templates built into Action Pack management. The final thing to note is that there's a hyperlink at the bottom of the 2nd page that goes to the design chapter. So if you're looking for more detailed information too, there's the place that you can be redirected towards. Moving along, we'll do a similar exercise, but now on the 4500. Now in the 4500, there's 2 main branches. There's the classic supervisors. That's the supervisors 2+. Through the supervisor 5, 10 gig E. That's not what we're covering in this specific section. Those are covered in the QoS SR&D, but here we're going to be focusing on the latest shipping supervisors, the 6E and the 7E, because these have a different QoS entirely. This is all using modular QoS CLI. So this is the evolution and the direction that we're going for all our switches. The 4500 can be found at the access layer. It can also be found at the distribution, sometimes even in the core. The access layer is where you're going to have the most variation in policies. Here's the main policies summarized: conditional trust, DSCP trust to trusted endpoints, as well as to on any given uplinks. There's no need to explicitly enable QoS on this platform. It's on by default. Remember, this is iOS QoS, the same QoS code that's on our routing family. On our routers, QoS is always on, and not only that, but DSCP, well, trust is always implicit too, so there's no need to explicitly enable that. The various models at our disposal and configuring egress queuing. There's really only 2 steps required to activate and deploy QoS on the 4500. Choose your ingress model and then configure your egress queuing. This is a policy that shows how we can apply conditional trust to a Cisco IP phone. We have to do the cost to DSCP mapping manually via a service policy, and that's what's being illustrated in this design example. And then just a single, actually, sorry, 2 commands that are applied on an interface basis. The QoS trust device Cisco phone, that's a conditional trust command, and then the service policy input command. If we want to have a more complex policy to do some explicit marking or possibly policing, well, again, these are defined globally, and then a single interface-specific service policy statement. For queuing policies, these supervisors offer up to 8 queues, with one of those queues being a strict priority queue. So taking advantage of the increased queuing granularity, now we can send our 3 strict priority applications, voice, broadcast video, and real-time interactive, to our strict priority queue. We have a dedicated queue for our control plane and signaling traffic as well as management. And then we can have dedicated queues for various application classes. It really then, takes advantage of the increased granularity for our provisioning. We can enable dynamic buffer limiting, which is a congestion avoidance mechanism, loosely similar to WRED. Basically, it starts aggressively dropping packets as the queue fills to capacity, and you can skew which packets are more aggressively dropped so that you'll make sure that your higher priority flows are serviced ahead of your lower priority flows within a given queue. We have a dedicated queue for best effort and also a dedicated queue for scavenger. Queuing policies are then shown on the next few slides. These are covered in line-by-line detail in the SR&D, so I'm not going to go through them now. And then when it comes to Ether channel, well, the ingress QoS policies are applied now on the logical port channel interface on this platform. However, the recommended policies for all Ether channel uplinks, downlinks, and same level core-to-core or distribution-to-distribution links is basically to trust DSCP. That's enabled by default. So basically, there's no explicit configuration required in order to achieve the recommended policies on the ingress. Egress policies, as always, are configured on the physical port members. So that hasn't changed. That's the same across all the platforms, and that's the same here on the 45. A 2-page at-a-glance summary for everything needed to configure QoS on the 45, SOUP 6, and 7, including the configuration as well as the link for more details in the design guide. Becomes iterative at this point, but we'll go on to our next major platforms and we'll look at the 6500. There's a whole variety of line cards available on the 6500. We're just going to present one design example here. All of the line cards supported by Medianet applications are detailed in the SR&D, but just to present a simplified design option, we're going to be focusing on the 6716 in this particular section, just to provide an example. And besides, that's the one that has the richest QoS features because it supports DSCP to queue mapping as well as an 8-class QoS model. So 6500 typically at a distribution or core layer of the network, in which case we don't have to worry about access edge policies. If it's deployed at an access edge, yeah, that is the case sometimes. We have all those models detailed in the SR&D. The point I'm just trying to make on this slide is that more often than not, it's at the distribution or core layer of the network. What are the steps to enabling QoS? To deploying QoS? Well, first is to explicitly, globally enable QoS. It's absolutely critical on this platform because it's disabled by default. Configure DSCP trust. That's going to be the policy in 80% or more of deployment cases. Ingress queuing, especially on line cards that are oversubscribed, and also then egress queuing policies, as usual. To enable QoS, simple, 2 words, MLS-QoS. To trust DSCP, interface-specific, MLS-QoS trust DSCP. And then all queuing policies are enabled on the interface. I do appreciate and recognize that that makes for a very, very long configuration. And not only that, interfaces, because if they're grouped together, share some common ASICs. So if you configure QoS policies for ingress or egress queuing on one interface, it will likely show up on 4 or 8 adjacent interfaces as well, depending on the line card that QoS is being configured on. It's an interesting twist on the ingress queuing policy on this platform, the 6716 line card. Even though it's DSCP to queue mapping, by default, you cannot modify the DSCP values that are mapped to the priority queue. Only EF and CS5 are being mapped to the priority queue by default, so we don't actually have the administrative option to map real-time interactive traffic, such as telepresence, to the strict priority queue. So we'll have to map it to a different queue. In this case, I'm mapping it to a queue that's also being shared with other video flows, rather than, say, mapping telepresence to Q7, which is a queue that's intended for control plane traffic. I don't want my video traffic to burst and overwhelm control plane traffic, so I'd rather separate the video from control. And then similar logic for the rest of the policies, as whenever supported, we take advantage of a default queue and a less than the best effort queue. Configurations on these pages, 2 pages. And all of these, as I mentioned, are interface specific. That's something that we are aware of and we want to simplify. And we may already notice that in some of the designs, for instance, on our next generation platforms like the Nexus, that's all being done globally, and then there's only a single service policy statement on a given interface. So that will be the direction for the next generations of 6Ks as well. Egress queuing model, now we can map all priority queue. We have a control plane queue with dedicated queues for other classes of traffic, a default queue, and a less than best effort queue. Very similar logic, and then the configuration. As you can see here, though, the configuration becomes increasingly complex and takes up a lot of space. So using a management tool to push this out not only scales your deployment, expedites it, but also then reduces potential human error just from typos in these policies. Ingress QoS, all we need to do is enable DSCP trust, and that's done on the logical port channel interface. Egress QoS, this is, as always, performed on the physical port members. An at-a-glance summary for deploying QoS on the 6K. Okay, so now with that, we'll shift our attention and we'll move over and look at WAN and branch QoS. So no longer the campus, we're looking at a completely different place in the network that uses completely different QoS tool set, completely different syntax for the most part, etc. How this all works is what we're going to be considering in this next section. Why do we need QoS? Well, this is probably the most accepted place for QoS. Like, we very rarely get any dispute as to the need for QoS in a WAN and branch edge because you're typically connecting LANs to much lower speeds, WANs, and as such, you're seeing significant downshifts in speed and ultimately bottlenecks. Congestion here occurs not just on a few millisecond basis like it does in potential congestion in campus scenarios, but it can be sustained congestion over several seconds or even longer, in which case we're dealing with managing not just packet loss, but also potentially jitter, that variation in delay from one packet to another. Most real-time applications have jitter tolerances in the order of, say, 10 milliseconds. 30 milliseconds of jitter in one-way direction, say, for voice over IP. However, that's also been expressed, and we recommend no more than 10 milliseconds per hop of jitter allowed. So we're controlling jitter and packet loss via our QoS policies on the WAN and branch. We want to make sure that we have similar and compatible policies and complementary policies to what's ever been configured on the LAN in the campus. Now, some of our platforms perform QoS in hardware. The ASR, for example, performs several of its QoS functions in hardware. However, on our ISR families, QoS is still performed in software. So recognizing that software QoS does entail a marginal CPU load. That load will vary on the policy, the complexity, the function, the speeds, the platform, the memory, so many elements that will determine how much of a increase in load will be placed. But just the network administrator should be aware that this is the case when we're dealing with the WAN and branch platforms. We want to enable queuing policies wherever there's a potential for congestion, as well as congestion avoidance, such as WRET policies to improve the throughput, especially for TCP-based flows. These are some of the considerations that we're going to be looking at over the next several slides. These are unique to the WAN and branch, and we have to have a clear idea of their potential implications as they affect the designs to follow. Let's look at each one in turn. Modular QoS CLI, MQC. This is the design syntax that we've been using in our iOS routers for, I'd say, about maybe not a dozen years. I can't remember exactly, but 10 to 12 years, I would say, we've been using this syntax. It's a three-part syntax. Class maps define the various flows that you're going to apply QoS policies on. Policy maps detail what exactly you're going to do to each given flow after it's been identified. And then the service policy statement binds that policy and attaches it to an interface and will specify whether the policy is to be applied in the input or output direction. Now, more recently, as of 12.2.20t, we've ported software from our distributed platforms onto our non-distributed platforms. And we've called this initiative the Hierarchical Queuing Framework, or HQF. The long story short here is that HQF allows for some new QoS twists and features that were not previously supported, some of which are summarized here. We can have multiple levels of packet scheduling, queuing policies within queuing policies. We can integrate shaping policies with nested queuing policies, so on and so forth. But the one I really like is the availability of allowing for a fair queuing presorter on any class. Previously, we could only apply a fair queuing presorter on the default class, but now we can apply that on any given class. I'll have some slides coming up that illustrate that graphically to graphically illustrate the logic of how that works. But basically, all this means is that we have a few more tools and options in our QoS tool set now since HQF. And again, that came in 12.2.20t, and it's embedded in iOS 15 mainline. Okay, let's look at each component of our QoS tool set in iOS, and we'll see how they interrelate, because then this will help us to design our policies effectively. I'm going to start back to front, if you will, from the final output buffer, and we'll work our way forwards. So let's look at the egress. Just before packets egress a router interface, they are buffered in what's called a transmit ring. The transmit ring is a final output buffer with the purpose of always ensuring there's a packet ready to be placed on the wire, thus driving link utilization to full capacity, 100%. So as packets come in, they're placed in the transmit ring. Typically then they're just serviced and packets never queue up. Once packets start queuing up, then the software recognizes that packets are arriving faster than they can be transmitted, and therefore there's congestion. Once the transmit ring fills to capacity, that's a signal to the iOS software to implement whatever queuing policies may be attached to that interface. The transmit ring may be tuned. By and large, we recommend leaving it at its default setting because these default settings vary according to hardware and platform. There's very few instances where it needs to be manually tuned. Typically, for instance, we've only found this to be the case on some ATM interfaces when deploying QoS for telepresence or other HD video applications. But with those very, very few exceptions, we recommend leaving the transmit ring at its default value. If it does need to be tuned, it's done based on an interface command as illustrated, TX ring limit. Incidentally, in the SR&D, there's also commands that show you how you can verify the size of a TX ring. And it's basically a show controllers command, pipe to include TX ring, and then that will show you the given transmit ring depth on any given interface. So that's all in the SR&D too. Now, fair queuing. Now, when we talk, say, class-based weighted fair queuing, or just fair queuing, it's actually a little bit of a misnomer because it's not weighted fair queuing, but rather it's flow-based fair queuing within iOS MQC. It was never weighted fair queuing. It was always flow-based. So what that means is that how many flows are contending for a resource, whether it's the interface bandwidth directly or contending for a queue that will then be placed into the interface. How many flows are there? In this case, we have 4 flows, and so packets from each flow will get 1/4 of the resource, whether it's, like I say, interface directly or a queue. A flow is identified by 5 tuples, identifying either a unique source or destination address combination, ports, or layer 4 protocol. All of these then combined will identify a specific flow. This is the same 5 tuples that are used for NetFlow. To enable fair queuing, well, like I mentioned previously, it was only an option on the default class and enabled with the fair queuing policy map configuration command. Now, class-based weighted fair queuing is a method in which bandwidth could be guaranteed to a given class of service. Not priority bandwidth, but a minimum bandwidth guarantee. Queuing policies, as we mentioned, only engage when the interface is congested. That's signaled by a full transmit ring. And then these buffers then become active, and the scheduler begins to select packets from the given buffer. So as packets enter the various queues, they're assigned to their queues by the policy map that defines the details of the class-based weighted fair queuing policy, and then they are dequeued from their respective packets based on the bandwidth or the percentage bandwidth that's been allocated to each queue. If a queue is not using its bandwidth, that bandwidth is dynamically allocated to the other queues available in proportion to their configured bandwidth percentages. Configuring class-based weighted fair queuing is a matter of using the bandwidth command in a policy map configuration mode. Bandwidth can be configured using absolute kilobits per second, or as a percentage of a link's bandwidth, or as a percentage of bandwidth remaining after the strict priority queue has been serviced. So those are your 3 options: absolute kilobits, or using bandwidth percent, or using bandwidth remaining percent. On top of that, then we have the option of enabling a strict priority service, and this is called low latency queuing. Originally, and more technically correct, it was named priority queuing class-based weighted fair queuing, PQ, CBW, FQ, but it was just too much of a mouthful to say and not very slick from a marketing perspective, so it was shortened to low latency queuing. Basically, it's the idea of adding a strict priority queue to the class-based weighted fair queuing algorithm for real-time servicing of packets. Now, what's really important to note and to understand is that when LLQ is implemented, it not only provisions a strict priority queue, it also provisions an implicit policer of traffic for that queue. Now, as I mentioned now a couple times, queuing policies are only active when there's congestion. Similarly, this implicit policer is only active when LLQ is active, which is only in the case of congestion. For instance, if I provision a policy for 1 megabits per second for voice, not only do I have a strict priority queue for 1 megabits per second worth of packets, but an implicit policer guarding admission to that queue. If I try to offer more than 1 megabits per second of voice packets to that queue, anything in excess of that will be dropped. Now, the advantage of this strict priority, this implicit policer for the strict priority queue is to protect the rest of the traffic. If low latency queues or real-time queues were unbounded, you could seriously starve out, and very realistically starve out the rest of the queue. So this is a way of containing and gating how much traffic is going to get that service, and it really does protect the remaining flows. It's very important to do that. Over a dozen years ago, we had a feature called priority queuing, which basically offered 4 levels of priority queuing. Strict priority, that would have to be exhaustively serviced before medium priority, which would be exhaustively serviced before normal priority, which would be exhaustively serviced before low priority. And what we found was that it wasn't very practical to deploy because it's just very often bandwidth would be completely starved from the lower priority queue. So it's very important to bind and place limits on that strict priority queue. This is how it's achieved, and this is completely in line with the RFC 3246, which recommends using policers to bind the traffic that's destined to a priority queue. Now, here's where it really gets interesting, is that people have been deploying low latency queuing for voice for many years. And now that we've come back and say, you know what, voice, absolutely, it's a strict priority application. People have gotten that. People have deployed that successfully with very high quality, etc. And now when we're saying, well, video traffic, like, say, telepresence, is 100 times more sensitive to drops than voice. Well, it obviously, if voice needs PQ service, how much more so does telepresence and other HD applications require strict priority service? Okay, well, most administrators accept that, but the biggest pushback is, well, what is that going to do to my existing QoS deployment for voice? I've got everything working. I'm very happy with the quality. I don't want to now turn on video and then have that video potentially overwhelm and burst and start dropping or affecting the quality of my voice packets. Well, the way to protect that is to use a multi-LLQ policy. What this means is if we configure multiple priority statements within our policy map, there's not, in fact, multiple low latency queues deployed. There's actually only a single strict priority queue, but with multiple implicit policers. Let's look at an example, for example. Okay, pardon the redundancy. But anyways, let's say here we have 3 separate classes of traffic that I all want to provision for strict priority servicing in iOS. So I need an LLQ. If I provision all 3 of these applications to a single LLQ, then if I bursted video traffic either in the real-time interactive class or the broadcast video class, those bursts could potentially cause drops to my voice traffic. And that's typically a very undesired behavior. However, if I have multiple priority statements, a multi-LLQ policy, as illustrated in the configuration on the top right. I provision, say, a specific amount of traffic for voice, 1 meg, broadcast video, 4 meg, for example, real-time interactive, 5 meg. Well then, packets in these three classes are provisioned on a first-come, first-served basis until they hit their implicit policing limits. At that point, every traffic class will police its own traffic, and that way will ensure that that low latency queue is never oversubscribed. And that's how we recommend deploying policies for these real-time application classes like broadcast video, like voice, like real-time interactive, without having them interfere with each other. Tested, validated, very successfully deployed all around. The final but one set of features that we need to talk about is our DSCP-based weighted read. This is congestion avoidance. Once the queue is filled to capacity, how do we make sure that traffic is dropped in accordance with our business priorities? Well, we do this by enabling DSCP-based WRED on a given queue, and how this works is for a given assured forwarding class, there are 3 drop precedence or drop preference levels. It's very similar to a traffic light. Traffic light, you have a conforming rate, traffic that goes when the light is green. You have a marginal allowance for excess or exceeding traffic, that's a yellow light. But then you have a clearly defined violation, which is red light. So in networking terms, the drop preference 3, we could illustrate that as traffic that's been marked in violation of a traffic contract. Yellow, AF drop preference 2, and then conforming traffic, AF drop preference 1. So as packets arrive in our queues, once we start hitting our weighted read thresholds, we begin dropping traffic marked drop preference 3 more aggressively than drop preference 2, which in turn is more aggressively dropped than drop preference 1. It's important to remember, though, that the R in WRED stands for random. So it is still a random operation, but the weights are skewed such that statistically a drop preference 3 is dropped more often than drop preference 2, which again is dropped more often than drop preference 1. And so that's the intended behavior of the assured forwarding traffic classes as defined in RFC 2597. To enable that on an interface, it's a simple random detect DSCP-based command. And then finally, what we're going to be seeing more and more is the reemergence of RSVP. Not at all for marking, policing, queuing functions at all, but simply and strictly for call admission control. So with call-oriented traffic, such as voice over IP, well, we could use non-network aware admission control mechanisms like location-based CAC or things of that nature, because voice traffic was so lightweight and so predictable and constant, so well behaved, we could get away with rudimentary mechanisms. However, with today's rich media applications, it's not the case. For example, let's consider telepresence. A telepresence call on a CTS 3000 based system with all the optional extras, it could run a single call, could run 20 megabits of traffic. If suddenly you have to make a go, no-go decision of 20 megabit flow onto your network, it'd be really good to have network awareness in making that decision. And therefore, the only protocol that has that capacity is RSVP. So we're really going to see a reemergence of RSVP. It's one of the 4 Medianet initiatives for research and development. The other 3 Medianet initiatives is auto-provisioning, is reporting such as media trace and management, and reporting and management, and there's one more. Auto-configuration, reporting and management, trace, and I apologize, the 4th one escapes me at the moment, but I can follow up with that. But long story short, we're going to see a lot more RSVP coming back into the picture as well as development on it. When it comes to our QoS rules across the WAN and branch, here's a summary of our policies. Basically, queuing policies at the WAN and branch edges, as well as DHCP-based WRED. We may have optional RSVP policies overlaid there too. Summarized, all these considerations, tools, and mechanisms are presented in this at a glance. And then we can go ahead and look at platform-specific implementation. So the ASR and the ISR G2. Very, very similar QoS configuration. So rather than, to minimize a bit of redundancy, we're going to consider them both at the same time. Where there are differences, we'll explicitly call them out. The ASRs are typically used for WAN aggregation boxes, and then the ISRs as branch routers. Basically 2 steps when configuring QoS on an ASR. For an ISR, there's only a single step required. The first step is to deploy our WAN edge queuing model. It could be 4, 8, 12, or any number in between. On an ASR, we may have to also, in certain circumstances, deal with potential internal oversubscription, and we'll look at how to address these as well. That's the only design difference between these two platforms. As we've already seen, we can have any number of QoS models. Because iOS QoS is very flexible, we're not limited to a set number of hardware queues. We can design any number of queues that reflect our business priorities. And so we'll illustrate this example. We could start, say, with a 4-class model, a very simple QoS model: real-time class, control class, data class, critical data class, and then the best effort illustrated in the white slice. As we increase the number of classes, what's important to keep in mind is trying to keep the relative bandwidth allocations as consistent and compatible as possible so that the application response times don't radically change from one model to the next, and the user base continue to receive a compatible level of service going forward. And as we continue to increase the complexity of our QoS models, we again keep on wanting to make sure that the subdivisions of bandwidth are overall in line with the main groupings of real-time, best effort, control, and critical data. Similar design recommendations as previously described. Limit our strict priority queues to 1/3 of a link. Minimally provision at least 1/4 of a link for best effort. Squeeze scavenger queues down to their minimums. Remember, if there's traffic and there's bandwidth available, this will be serviced, but as soon as there's congestion, you are going to be starting to drop traffic. So what are you going to drop first? Typically, scavenger is the prime low-hanging fruit to make that decision because it doesn't belong on your networks anyways. We recommend enabling fair queuing presorters on all classes except for control and scavenger. Those don't need the extra configuration as well as the extra processing. Control traffic, you want to provision on first come, first serve. In scavenger, there's no implied good faith guarantee, so why waste routing resources by making sure that those flows are equitably contending for that queue. On the ASR, you may want to expand the queue limits. We detail this in the SR&D, especially depending on the speed of the interface that you're connecting to. Enable DHCP-based WRED on all assured forwarding classes, and here's some sample recommendations that we offer. Basically, start dropping traffic marked AF3, AF drop precedence 3 at 60%, 70% for drop precedence 2, 80% for drop precedence 1, and the maximum thresholds all at 100. Putting this all together, what does our policy look like? Well, it's summarized on these following slides. This is a 4-class model, followed by 8-class model, followed by a 12-class model. Obviously, the more complex the model, the longer the policy, but what's nice is that when applied on an interface basis, it's only a single line that needs to be applied on the interface. The rest is globally configured. Finally, on the ASR 1K, there is a potential for oversubscription within the architectures. Some of these scenarios are presented on this slide. Basically, when you have a certain amount of SIPs cards that say are 10 gigabit each, and yet you're connecting into like 4 SPAs into one SIP, for example, you have a 40 gig potential that's being connected into a 10 gig trunk and across the plat plane, etc. So there is this potential for internal oversubscription. How do we make sure that our priority traffic is not dropped? Well, there is also internal queuing policies that can be configured. You can see here that the configuration is not significant. It's just a few additional lines. Whether it's SPA-based or SIP-based will depend on the interface type. For instance, I believe the ATM and POS are SPA-based, whereas Ethernet-based, Gig Ethernet-based interfaces are SIP-based. These are all detailed in our SR&D, but just adding a few additional lines of configuration, make sure that all the bases are covered and that from beginning to end, strict priority traffic is treated in a strict priority fashion, both internally as well as externally. These at-a-glance documents then summarize the considerations and deployment recommendations as well as configuration details for the ASR and then the ISR. The only difference between the two is that internal oversubscription on the ASR. That then summarizes the presentation. Basically, what we've covered is that traffic is continually to exponentially increase on our networks, and it's really shifting away from traditional traffic pattern to reflect the dominance of video on our networks. How to deal with all these multimedia applications is recommendations that we recommend following the IETF RFC 4594, because that's not a Cisco-specific set of recommendations, but rather that's an industry-wide set of recommendations, allows for greater intercompatibility with service providers, partners, extended networks, etc. You need QoS in your campus. Why? Primarily to control packet drops. If you have 10 milliseconds worth of congestion, which is very, very possible, especially due to the nature of bursty nature of video, you can overrun buffer capabilities on even the deepest and richest buffer line cards that we offer. So to prevent that scenario and to prevent drops from appearing, remember only 1 in 10,000 will be visually apparent to the end user, you need to implement QoS policies within your campus. We reviewed various trust states, logical versus physical QoS, port-based, VLAN-based, or Ether channel QoS, how and when to implement the various policies, as well as detailed recommendations for both ingress and egress policies. In the WAN and branch, we're going to be controlling not only drops, but also variation delay, also known as jitter. We have a different tool set at our disposal in this place in the network. It's iOS-based QoS. It's different from Catalyst hardware. We've gone over the tools like the TX ring, class-based weighted fair queuing, low latency queuing, along with its implicit policer, how all these tools all optimally fit together to come up with the recommended policies for rich media networks. And then finally, just a running theme and a recurring theme in this presentation is that not only do we have the detailed, multi-hundred-page design guides at your disposal for reference, but more recently these at-a-glance summaries that allow network administrators to get the gist, the salient points, the cliff notes or Coles notes, if you will, cheat sheets of what you need to know for a given place in the network deployment and a platform-specific deployment. There's also an Auto-QoS for Medianet feature. That's detailed in the appendix of this deck. I've sent this deck to our folks, Mike and company at Action Pact, and they'll be posting that, and they'll be sending out, I believe, a follow-up email, I'm told. A summary of the at-a-glance guides that we discussed in this presentation are listed on this particular slide, as well as if you need more detailed information, the full design chapters are then listed on this slide. Now, I don't know how are we okay for time to keep on going through the appendix, or?
We're okay, Tim.
We're okay? Okay, then. If you like, I'll round out my time by considering this Auto-QoS for Medianet tool. And this is a tool very similar to, the previous generations of Auto-QoS. And instead of limiting the scope to automatically provisioning the tested and validated best practice design recommendations just for IP telephony, it supports much more than that. Currently, it's only available on the 2K, 3K. However, there is development on it currently on the 4K. I do not know when that's going to ship. That's something that's up to the product team and their relative priorities. But I do know I've been involved in that design, and that is in the works. How this works is, with a single command, a network administrator can deploy a variety of Auto-QoS models. For instance, Auto-QoS VoIP to support Cisco IP phones. These are, our physical endpoint units, or Cisco soft phones, or just to have Auto-QoS VoIP Trust. These first set of commands, Auto-QoS VoIP with the various keywords, are to provide backwards compatibility. That's their function. Auto-QoS Trust is another option. Basically, it'll just configure trust of either CoS or DSCP, along with all internal and ingress and egress queuing policies. A new set of features is Auto-QoS Video, so providing conditional trust for Cisco telepresence systems or Cisco IP cameras. Another design option that an administrator has is to say Auto-QoS Classify. And with one command, it'll configure access lists, class maps, policy maps to configure all these classes of traffic. All of this can be viewed as a template. A network administrator can override, can delete, access lists, can add to the access list for various class, can add more classes of traffic or even less. So basically, it can be viewed. It's really important to view this as a potential template, not necessarily a final solution, but something that can be tailored and customized to a specific deployment environment. The Auto-QoS Classify option has a potential keyword support for policing. So you could automatically not only classify marked traffic, but also police it at the edge, all based on our latest validated designs. And again, all these rates can be modified, so if you want to police to a different rate or with a different action, whatever the case may be, that can all be overridden. And yet, using Auto-QoS to that end can really significantly accelerate the deployment, expedite it, and reduce the potential for errors coming and arising from, say, typos or manual configuration. Not only will Auto-QoS provision all these ingress QoS policies, including ingress queuing, but then it will automatically provision egress queuing policies according to the best practices as well. That's all done automatically. Let's look at some examples. If an administrator configures Auto-QoS Trust, then in addition to the egress and egress queuing that's not shown in this slide but will be shown on subsequent slides, within the interface you'll see it'll configure Auto-QoS Trust CoS on a layer 2 switch port, but if it's a layer 3 routed interface, then by default it'll trust DSCP. The administrator can go in and change that. If he wants to trust CoS all the way, regardless of whether the switch port is layer 2 or layer 3 routed interface, he can override that. But by default, layer 2 switch port will be trusting at layer 2. A layer 3 routed interface will be trusting at layer 3. Auto-QoS Video CTS, if that's entered into the config, then it'll expand that to Auto-QoS Trust Device CTS. That's a Cisco telepresence system. It'll trust at layer 2, and then provision Auto-QoS Video CTS. Oh, I'm sorry, that's a command to enable it. Another option is Auto-QoS Video IP Camera, and again, it expands the interface commands. In this case, now it'll trust DSCP. Auto-QoS classify will provision automatically, like I say, access lists, class maps, and then policy maps to identify all these various application classes and then to mark per RFC 4594 values, AF41 for multimedia, AF11 for bulk, so on and so forth. Auto-QoS classify police gets even more complex because now we're introducing not only marking on a per class basis, but also policing on a per class basis. If we wanted to maintain backwards compatibility using the Auto-QoS VoIP models, well, there's three options: Auto-QoS VoIP Trust, Auto-QoS VoIP Cisco Phone, or Auto-QoS VoIP Cisco Soft Phone. So the logic of each deployment option is illustrated in these diagrams. And so, for instance, if we look at Auto-QoS VoIP Cisco Phone, it's going to mark, first of all, identify voice flows, mark them to EF, and then also police them. The logic there being is that no, Cisco Phone is going to generate more than 128K of voice traffic. If you're receiving more than that, then there's some attempt at a compromise or security vulnerability there. Perhaps somebody's spoofing CDP and then wants to just gain access and hijack and ruin the quality of your intended priority queues for voice. Similar logic then for signaling traffic, and then finally best effort traffic. Ingress policies automatically configured, as well as egress policies. The full details of the configuration are illustrated in the subsequent slides. And then something that administrators, just before I get to that, the ingress queuing policies are identical to what we've already covered for these platforms, as well as the egress queuing policies. We've already gone over this. All automatically configured just with one interface-specific command. But what most administrators, sometimes when they enable Auto-QoS, because there's a lot of global configuration, they at times might feel overwhelmed at that and say, well, I don't understand all of this, so I just want to negate that. And I type in no Auto-QoS VoIP on the interface to remove it, but then they're surprised that all the global configuration remains. And that is sometimes a cause for concern. In the SR&D, I've included a configuration example that shows how to remove entirely Auto-QoS. So just by cutting and pasting that section, can do a complete removal if that's so desired. The reason is that even if Auto-QoS is enabled or disabled on a specific interface, you don't want to be adding and removing some of the global QoS settings, because as those buffers are reallocated and recarved, they can, on certain platforms, disrupt service. So you don't want to be constantly disrupting the service. That's why the global policies have been designed to be retained, so that if an administrator adds or removes Auto-QoS on a specific interface, that's not going to disrupt or result in service disruptions. Long story short, there's the at-a-glance document for Auto-QoS, as well as then the link to the SR&D is at the bottom of the page for that, for even more details on that feature. Currently on the 2K, 3K, but coming on more. Okay, then that, all in all, covers all the material that I have. And with that, I guess I'll bounce the ball back over to you, Steve.
Thank you so much, Tim. Excellent. We'll now open the floor to questions, and feel free to submit the questions via the Q&A panel or the chat panel on your WebEx controls there.
So one of the questions from Aaron Polk, will the slide deck be available? Yes, Mike assures me it will be. And it will be available not only, or at least I forwarded in its full version, PowerPoint version, so hopefully that's the one that will be available rather than, say, an Adobe PDF copy, because then the animations will be lost.
Yeah, there's a question that just came in. What about the audio? The entire recording of this webinar will be available on our website. You mentioned that the Cisco telepresence data is prone to packet drop more than, let's say, voice traffic. Why does in the priority-wise, voice is still higher priority than telepresence traffic?
Okay, so I wouldn't necessarily say that telepresence is prone to more packet drops. I would perhaps phrase that as it's more sensitive to packet drops. Like I mentioned, 1 drop in 1,000 is visually discernible to the end user, whereas voice, our target for packet loss, is 1 drop in 100. And I'd like to clarify then, if I've made the impression that voice is a higher priority than telepresence, that's not my intention. Per RFC 4594, there are 3 classes that may be supported with a real-time expedite forwarding service. It's voice over IP, real-time interactive, which is a class we use for telepresence, and broadcast video. As illustrated in the low latency queuing multiple LLQ slide, these 3 classes may be provisioned with strict priority service, but they're service on a first-come, first-served basis. It's not that voice is serviced ahead of telepresence, which may or may not be serviced ahead of broadcast video. That's not the case. They're service on a first-come, first-served basis with strict priority according to their limits. So whether that limit is an implicit policer or a call admission control function, it's first-come, first-served, strict priority servicing. There's no hierarchy between these 3 real-time applications. They're all equal. Now, with that being said, too, I'll make another comment. On some platforms, you'll start seeing the support for multiple priority queues, which is the idea of, okay, there's one, for instance, one priority queue might be used for servicing voice, and then once that's explicitly serviced, then you support another priority queue, and then the rest of the queue. So that's a structure that's starting to make inroads. It's not strictly consistent with the RFC definition for the EF per hop behavior. Again, that's RFC 3246. However, that is a feature that some customers have been asking for, and it was basically to address this. We want to make sure that our voice that's rocking and rolling and is really, really good is not affected if we do start putting video into, like, say, strict priority services. So they kind of modify the definition of what strict priority is and implement that and offer more options. So that is something to be aware of.
Tim, we have another question. Will the class-based quality of service be enhanced to support DM VPN-QoS statistics?
Yeah, so class-based QoS, there are some additional support options. For instance, per session QoS was a feature that was, in line with the needs unique to IPsec VPNs and DM VPNs in turn. For statistics, I don't know exactly what you had in mind, but basically you can still monitor all the statistics on a per class basis because the DSCP values are always preserved in IPsec tunnels, which include DM VPN. So whenever the packet gets encapsulated with the encryption overhead, that IP toss byte is preserved, and therefore the per class statistics can still be monitored even though the traffic in the payload is encrypted and no longer visible. Or the TCP, UDP ports and addresses, destination and source IP addresses, all of that is encrypted at that point, but the toss byte is preserved, so you can still monitor statistics on a per flow basis. No QoS support on 2960 cat switches. That's not correct. There is full QoS support on those switches. Everything that I covered on the 3K, the 3560 and 3750, is equally applicable both in function and in syntax on the 2960 switches. The only exception is that the 2960 switches do not support ingress queuing. That's the only difference. Can you suggest a good resource to use to learn how to implement RSVP? I would recommend going to the latest QoS SR&D, the WAN branch chapter. It was linked to near the end of this deck, and then there's a section on there for RSVP, both at the operational level, the protocol behavior as well as in configuration options. Right now, RSVP, like I say, is still fairly limited. There's a few things. The real advantage and use of RSVP is for counting. So counting how many calls are already on a link and the bandwidth for these given calls to make a very intelligent, network-aware admission control decision. That functionality is going to be continued to be enhanced, and so look for more of these types of features coming.
Thank you, Tim.
Sure, my pleasure. Okay, doke. Well, then as a final note, my email's on the front of the presentation. If there's questions specific to the presentation, I'll be happy to answer them by email. I will qualify that. I'm not able to scale to provide, one-on-one extensive support, consulting support for a given scenario. But if there is questions relating to this deck in particular, I will answer them. It usually takes me a few days to get through all emails, but I do answer every email. Anyways, hope that helps.
I think there is one other question that just popped up here. Yeah, we still have a few.
Yeah, I saw it. Is it okay to put voice and call signaling in the EFQ? Yeah, absolutely. It is possible. It's not necessary, okay, because voice has different service level requirements from signaling. For instance, voice has a one-way delay budget of 150 milliseconds. It has a one-way jitter budget of 30 milliseconds, which we also then try to limit to 10 milliseconds of jitter per hop. And then it also has a 1% packet loss requirements. Call signaling doesn't have any of those requirements. It's a different protocol typically. For instance, if it's skinny, then it's a TCP-based protocol, ports 2000 to 2002. TCP doesn't need the same type of real-time servicing as VoIP. The other thing, too, is from a provisioning perspective, voice is very, very well behaved. You know exactly the number of packets and exactly how often they're going to come, so you can provision those voice queues to the kilobit per second very, very granularly, and you can do that. Signaling traffic, well, it's TCP, it's data, so that traffic can vary. It's typically quite lightweight, but still it doesn't have the same real-time requirements as voice, and it is not as explicitly and mathematically predictable as voice. So for those reasons, we recommend to provision with another class of service. But the short answer to your question is you can put them, it is okay to put them in the same queue. You're just giving a level of service of signaling that it doesn't necessarily require.
Thank you, Tim. I see there's another question that came up. What is the best way to measure the quality of service limits, classes, stats, queuing, SNMP, via SNMP or NetFlow?
The best way to measure quality of service stats, limits, drops, etc., is all polling via polling the class-based QoS MIB. You're going to get a lot more granular information for that. And then this product, Action Pack Software, does a fantastic job of polling that MIB and presenting that information via GUI. NetFlow provides different types of information. It's mainly more applicable to, say, traffic profiling, capacity planning, and so on and so forth, to give you an idea of the nature of the flows and the volume of any given flows, aggregate and individual across a given link. But specific to the stats that you asked for, queue limits, classes, stats, queuing, all of that, the answer is SNMP of the class-based QoS MIB.
Thank you, Tim.
Sure.
Just want to thank everyone again today. Thank you, Tim, and we can adjourn for the afternoon.
Great. Thanks so much, Steve. Thanks, Mike, for setting this up, and thanks, everyone, for taking the time to attend. I really appreciate that. And again, there's the resources, and all the best with your QoS deployments.
Thanks again. Have a good afternoon.